What specific problem does your proposed two-stage framework aim to solve in the context of hallucination detection, and how does it differ from existing methods?
The proposed two-stage framework aims to solve the problem of balancing latency and interpretability in hallucination detection, which is critical given the limitations of existing methods that often lack interpretability and can introduce significant latency due to the size of large language models, LLMs. Unlike conventional methods that utilize LLMs as end-to-end solutions, our framework employs a small language model, SLM, for initial hallucination detection, followed by a constrained reasoner LLM that provides explanations for the detected hallucinations. This two-stage approach allows for quicker initial detection while still leveraging the reasoning capabilities of LLMs for interpretability. Additionally, we address the inconsistency between the SLM's decisions and the LLM's explanations, which is a common issue in self-rationalization models. By implementing a flagging mechanism and categorizing hallucinations, our framework enhances the alignment between detection and explanation, ultimately improving user trust and the overall effectiveness of hallucination detection.
Can you explain in detail how the proposed two-stage hallucination detection framework works? Please illustrate it step by step, including the role of both the small classification model and the constrained reasoner.
The proposed two-stage hallucination detection framework operates through a systematic process involving a small classification model, SLM, and a constrained reasoner, LLM. First, the SLM is employed to detect potential hallucinations from a given text source, denoted as X, generating hypotheses, Y. The SLM outputs binary labels, J, indicating whether each hypothesis, Y_I, is a hallucination or not, resulting in a subset, H, of detected hallucinations. Next, the constrained reasoner takes over, receiving the original text, X, and the flagged hallucinations, H, as input. Its role is to provide explanations for each detected hallucination, producing a set of explanations, E. The constrained reasoner operates under the constraint that the hypotheses it is explaining are indeed hallucinations, as determined by the SLM. This two-step process not only enhances interpretability by providing reasoning for the SLM's decisions, but also addresses latency concerns by utilizing a smaller model for initial detection before engaging the larger LLM for detailed explanations. The framework also incorporates mechanisms to identify and filter inconsistencies between the SLM's detection and the LLM's explanations, ensuring that the reasoning aligns with the upstream decisions, thereby improving overall reliability and user trust in the system.
Provide a simple example that demonstrates the inner workings of your proposed algorithm. Walk through the detection of a hallucination and the subsequent explanation process.
To illustrate the inner workings of our proposed algorithm, consider a scenario where the grounding source, X, contains factual information about a historical event, and the model generates a hypothesis, Y, that states, the event occurred in 1990. If this statement conflicts with the source, X, it is flagged as a hallucination by the small language model, SLM detection module, D, resulting in a binary label, J, indicating that this hypothesis, Y_1, is a hallucination. Subsequently, this flagged hallucination, H, is passed to the constrained reasoner, R, which generates an explanation, E, for why the hypothesis is considered a hallucination. For instance, R might output an explanation such as, the event actually occurred in 1985, thereby clarifying the inconsistency. This two-stage process effectively balances latency and interpretability, allowing for a rapid initial detection, followed by a detailed reasoning phase that enhances user understanding of the hallucination.
What are the theoretical or practical advantages of using your two-stage framework compared to conventional hallucination detection methods? Please discuss aspects like efficiency, accuracy, and user trust.
The two-stage framework proposed in our study offers several theoretical and practical advantages over conventional hallucination detection methods. Firstly, it balances latency and interpretability by utilizing a small language model, SLM, for initial detection, which is computationally efficient, followed by a larger LLM for detailed explanations, thus addressing the latency challenges faced by traditional LLM-based methods. Secondly, our framework enhances accuracy by implementing a constrained reasoner that provides explanations specifically for detected hallucinations, allowing for a more focused analysis and reducing the risk of misinterpretation. Additionally, the incorporation of a flagging mechanism in the reasoning process improves user trust by transparently signaling inconsistencies, which conventional methods often fail to address, thereby fostering a more reliable user experience. Finally, the categorized approach within our framework demonstrates strong potential as a feedback mechanism, effectively identifying false positives and refining the detection process, which is a significant advancement over the less adaptive conventional methods.
How did you design the validation process for your method? Describe the datasets, metrics, and human evaluation techniques you used to demonstrate the effectiveness of your approach.
The validation process for our method involved a comprehensive experimental design utilizing 4 datasets: NHNET, Fever, HalluQA, and Hallucim, with a complete test set from NHNet and a sample of 3,000 data points from the other 3 due to resource limitations. We employed human evaluation techniques where annotators assessed whether each explanation generated by the constrained reasoner accurately explained why a hypothesis was deemed a hallucination or justified it as non-hallucination. The effectiveness of our approach was measured using precision and recall metrics, particularly focusing on the performance of the categorized approach in identifying real inconsistent reasonings through a flagging mechanism. This approach demonstrated a significant reduction in inconsistencies, achieving a post-filtering inconsistency rate as low as approximately 0.1 to 1%. Additionally, we calculated a macro average F1 score of 0.781 for the categorized approach, indicating its strong potential as a feedback mechanism for refining the upstream detection model.
What specific results did your experiments yield regarding the performance of the categorized approach, and how do these results highlight the strengths and weaknesses of your proposed method?
The experiments demonstrated that the categorized approach significantly reduced inconsistencies between the upstream detection and the constrained reasoner, achieving a post-filtering inconsistency rate as low as approximately 0.1 to 1% across all datasets. This approach effectively categorized the majority of inconsistent reasonings under the specific Hallu_12 flag, facilitating easier filtering and mitigation for downstream usage. Additionally, the categorized approach outperformed the fallback method in identifying false positives from the SLM, achieving a macro average F1 score of 0.781, indicating its strong potential as a feedback mechanism for refining the upstream model. However, the fallback approach exhibited poor recall, often failing to signal inconsistencies, which highlights a weakness in its ability to effectively manage discrepancies. Overall, the results underscore the strength of the categorized approach in enhancing consistency and providing valuable feedback, while also revealing the limitations of simpler methods in addressing inconsistencies.